Hello, everyone. Welcome to today's live broadcast, a fast and novel chromatography-free forensics toxicology urine screen with DART-MSMS. I'm Shannon Stoltz, Senior Editor of Special Projects for LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Bruker. The new Bruker Applied Mass Spectrometry division is focused on the unique needs of the company's users, with a focus on the food, environmental, forensics, and clinical research and industrial markets. Analytical areas such as characterization, safety, authenticity, adulteration, QC of starting and finished goods are amongst the applications covered and are used across industrial, government, and academic institutes. The Bruker Applied Mass Spectrometry division is dedicated to helping provide complete solutions for the unique needs of end users. So we do have a few important announcements before we begin today. First, this webcast is designed to be interactive, so we do encourage you to ask questions throughout the event. You can submit your questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can enlarge the slide window by clicking on the small icon in the bottom right corner of the media player, and the slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget that's in the top right of your presentation window. I would now like to introduce today's speakers. We are very pleased to be joined today by Terry Bates and Francois Esportillo. Before joining Bruker, Terry earned his PhD under the supervision of Dr. Gavin Sachs' lab at Cornell University, where his work focused on the development of novel extraction geometries and rapid throughput analysis for trace-level analytes in complex matrices, using solid-phase, mesh-enhanced sorption from headspace direct analysis in real-time mass spectrometry. And Francois brings over 25 years of expertise in LC-MSMS applications. He earned his BS and MS from the College of William and Mary in Virginia and received a PhD from Rutgers University, followed by a postdoctoral position at Rensselaer Polytechnic Institute. He joined Bruker Applied Mass Spectrometry in 2021 as the DART-MS and Triple Quadruple Application Manager. So thank you both so much for joining us today, and please get us started.
Yes, thank you very much for this introduction. We are pleased to welcome you to the Bruker Application and Development Laboratory in Billerica, Massachusetts, just outside of Boston. And today we have this privilege to show you some interesting development that we are working on in the field of chromatography-free workflows. IonSense was purchased by Bruker about a year and a half ago, and as such integrated this new era of chromatography-free workflows into toxicology. We're using DART, which is a device to introduce samples into the mass spec, just like a different source, which we'll be discussing a little bit later into the program, coupled with mass spectrometry, triple quad in this case. And today's focus will be on toxicology screening. Very specifically, we're going to be working with stimulants for our first assay that we are developing here in the lab. So without further ado, I'll show you what Terry Bates is going to prepare for us. And I am going to show you a couple slides first just to frame the discussion that we are having today. So bear with me for a second here. So like I said, today we're going to be focusing on stimulants using DART, combined with a partner of ours, PinPoint Testing in Little Rock, Arkansas, that provides a product called ToxBox, which is a pre-prepared set of calibrators and QCs to help people in this field simplify their workflow. The primary goal is really to enhance data quality by combining mass spec with chromatography-free workflows, and also simplifying the whole workflow as such. The secondary goal is to include high-quality commercial kits into this process to lower the threshold of entry into mass spectrometry. It's often very difficult to start from scratch, especially in the smaller labs, if you are trying to include mass spectrometry into your workflow. And by using kits like that, we found it's a lot easier to perform this kind of analysis with people that may or may not be specialists in the field. So the agenda for today, we're going to look at sample preparation. Next, we're going to be looking at loading and operating the DART-MS, at which point I'll be discussing what exactly is DART and what how it's coming to replace LC and a HESI source, for example, into this kind of environment. We'll show you some data that we've generated, and we'll go to question and answers at the end of the program. So without further ado, let's go back to Terry. Hopefully you can see Terry right now. And Terry, you're on. I'll be narrating what Terry's doing. First, we'll be looking at the ToxBox kit itself, which contains a plate with the sample, the calibrators, the QCs, solutions to help us prep the plate, and a variety of other buffers and such that are used during the process. Next, we'll be looking at prepping the box itself. So the box comes to the customer frozen and has to be thawed. Prior to the this seminar, we took the boxes out about half an hour ago. They had time to thaw, and now Terry just opened the box, which contains calibrator sets and QCs. Samples will be added by the user, of course, but the box itself will contain the majority of all the kit, the items needed to process the samples in question. So first, the calibrators can and cannot come with matrix. In this case, they don't. So we'll be adding urine to our calibrators and our QC samples. For the purpose of this seminar, we will not be using real samples. We'll be using mock samples, which is a little easier. So normally what would happen next after loading the QCs and the calibrator urine matrix, the user would then use, of course, would then be loading, of course, patient samples or some kind of outside sample for this process. Of course, this is at this point research only use. So following the addition of the samples and the matrix, we add some water to dilute the sample a little bit and make it more amenable to the addition of a gluconide enzyme to remove the glucuronide samples from, glucoside moiety from the drugs to reduce everything to parent species. Following the addition of the enzyme and the water, the plate is then capped again and added or put onto a shaker so that we can incubate and let the reaction process. Typically, the reaction takes about half an hour or so. And we are going to then skip that step. Obviously, this is more of a shake and bake type of presentation. So once the system has been, the plate has been put on the shaker, we wait about half an hour at moderate shaking speed, followed by removal from the plate. So next, as most of these type of workflows are typically look like, we'll be adding a quenching solution to stop the reaction of the enzyme and also help precipitate the enzyme so that the sample remains cleaner for the next steps. So here we add the quenching solution, and we're only doing a couple of rows, of course, just to simplify things today. And the plate is then being resealed, and then we will be shaking the plate again to make sure we mix the solution thoroughly. So following that comes the liquid-liquid extraction, which will result in a cleaner extract for our analysis. DART, just like many other technologies, requires or prefers cleaner samples. In this case, and we'll discuss that a little bit later too, DART is actually a little bit more finicky than LC because there is no separation. So you cannot remove complete separation of analytes and leave the matrix in the system and be able to do analysis, especially for quantitative work. For qualitative, yes. For quantitative, not so much. So we do an extensive prep in this case to remove the matrix so we have a clean extract at the end of the process. So right now, what you're seeing is Terry's actually added the organic solution to the wells and is now mixing the organic solution with the sample in order to extract the analytes of interest. The solution used is a blend of different solvents, and its main goal is to have a very wide extraction capability, going from fairly polar to highly nonpolar compound. In this case, we target from as low as morphine and some of the early eluders and LC World opiates, all the way to THC and everything in the middle. This takes about 10 or 12 up and down motion with the pipetter to mix everything thoroughly. And once it's done, then we'll let the plate sit for about 10 minutes to allow for complete phase partitioning between the organic and the aqueous moieties. All right, so we're gonna speed up that test. We're not gonna wait 10 minutes. So now we're ready to remove the lower part of the sample, which is about 500 microliters of aqueous at this point. Oops, sorry about that. And these will be placed, the lower fraction will be discarded, and we're going to keep the upper fraction. So lower fraction has now been discarded. And the next step will be to take the plate to a blowdown system to evaporate the organic solvent. We typically evaporate to dryness, although that step can be modified depending on the type of compounds you work with. But in this case, we'll be evaporating to dryness and reconstituting in a solution also provided in the kit. All right, so the last step is we're now at hand. We have the solution ready to transfer, and at this point, we're about to transfer the solution, or the extract in this case, from the wells onto something that is fairly novel, which is a DART screen. Now, DART is a little different than your traditional LC environment, and what this will do is transfer then a very small amount, about 1 microliter or 2 microliters at most, of the extract onto a screen, which will then be utilized to introduce a sample into the DART-MS. So as you can see, Terry's about to transfer a very small amount of sample onto the screen, and then that very small sample needs to be dried out for a few minutes. It depends a little bit, of course, on the makeup of the solvent, whether it's mostly organic or mostly aqueous. Though if it's mostly aqueous, it'll be longer. Mostly organic will be much faster. We'll show you what the screen looks like in a second. Basically, it's a metal mesh that is being sandwiched between two stainless steel plates with discrete holes through the plates, so that the DART stream can then be pushed through the system. As you can see, there are 96 holes, and each hole is corresponding to a well from the deep well plates. So it looks very similar, but it's also very different. These are screens, so you can actually shoot a stream of ionized gas through each well, which will then be allow it to enter the mass spec itself. All right, that's it for the prep. As you can see, it's fairly quick. We are going to talk a little bit about the next step here, and the prep is fast, which is one of the big important things for us. DART is a really fast analysis technology, but because we have to have a fairly clean extract in this specific case, we have to do a lot of the prep ahead of time, by 96 well plates. So the idea is to have a fairly straightforward prep, something that's not going to take too long, and that will result in a clean extract that can be put on DART. As you can see, we just talked about using urine extraction, the plate, and then we go to the DART-MS system. The next step will be loading the plate on the DART-MS itself. But I think this is a good time for us to take a quick break from the lab and go to slides and look at what exactly is DART. So DART has been around for a while, and it's this device here that looks the blue gun here. DART has been around for about 17 years, pushed through with a company called IonSense that then became part of Bruker. The idea is to simplify sample introduction into the mass spec environment, and DART stands for direct analysis in real time. And the idea is to have a soft ionization that will primarily generate N+1s rather than adduct, for example. So DART has used inert gas. It's stable. DART is in a standby environment using nitrogen gas. And for running or doing the analysis, we switch to helium. Helium is the gas of choice in most cases because it allows for the formation of metastable species, which then transfer the energy from the electric discharge that creates the plasma here into the gas stream. And between the ionized helium and transfer of energy to water molecules, you end up ionizing your sample, which is located between the tip of the DART and the entrance to the mass spec. We replace the HESI source or the APCI source with a DART source. The DART source encompasses the whole DART gun and the attachment to the mass spec itself. Between the two right here is a grid that you just saw Terry holding, and that grid contains the sample. The DART will move from spot to spot, and we'll show that in a few minutes. And as the DART moves from spot to spot, it switches from nitrogen, which is our standby gas, to helium, which is our analysis gas. The reason we switch back and forth is to minimize the use of helium. Helium is a very expensive commodity these days, and the concept here is to only reuse helium whenever needed, so during the analysis. The analysis is quite short. We're talking between 5 and 30 seconds, typically, which allows us for so small use of helium and really fast analysis time. The species that are being ionized will then enter the mass spec and just behave like any other ionized species that you have with a HESI or an APCI. So really the novelty here is the front end of this ionization technique rather than what happens afterwards. What happens afterwards is pretty straightforward. There are a couple of things here, like this grid, which allows, it's an electrified grid, which allows for some cleanup of the source material so that fewer species than, few of the background species, I should say, are retained and do not enter the mass spec. If you want to compare what DART does in terms of ionization technology or technique to other sources, here you have it. DART is fairly centric in terms of polar to non-polar. It also has a maximum of about 1,000 to 1,200 molecular weight. So while other species can go much higher, DART really does not go above 1,200 typically. But it's got a fairly good range of analysis, which allow us really to work with most of the small molecules that are common in today's various fields of pharma, for example, or environmental. We'll do a lot of work in explosive detection. So basically, most small molecules will be detected via DART, or analyzed via DART, I should say. Because DART's been around for a long time, you have a vast amount of publication out there, and if anybody is interested, we're more than happy to supply you with references to your specific field of interest. But it's DART has been put on many different types of systems besides triple quadrupole, including exact mass or high res, for example, for a variety of analysis. The move to triple quadrupole mass spectrometer is kind of recent, which is really what we're debuting right now. All right, with this short introduction to DART, we're going to move to the next part, which is loading and operating a DART system. So we're going to go back to the camera here for a second, if you bear with me. All right, and I'm sorry, All right, just 2 seconds. We had a little camera issue this morning, so I apologize for that. And I'm going to show you what DART looks like in real life. And we're going to have Terry operating the DART as we speak. So I don't know if you can see the screen. Hopefully you can. This is the software we use, the TQ software, the mass spec software from Bruker. And this is a batch. I'll try to zoom in a little bit so you can have a better idea of what we're looking at here. So we have a batch set up. On the bottom right, the system is ready to run. Apparently, there's everything's blue on the screen, and we are now fired up the DART. DART is a very fast device, and you can see the deflection, which is not a peak. Let's not call this a peak. It is not a peak. There's no chromatography here, so it's more of a signal. Let's back off a little bit. I want to show you how the DART really works, which is really the novelty part here, because as far as the analysis itself, we are really running a very similar analysis to what would be an LC-MS type setup, given the fact that we're using the same exact kind of software. All right, so the DART is running right now, and very shortly we will see the DART plate move. The plate at the bottom left of the screen there in front of the DART gun itself is driven by a motor that has XY axis configuration, and we're going from spot to spot, not to say well to well, since this is not a well, but we're looking at different spots. So we spend about 10 to 20 seconds per well. There's a lapse of time between each well, primarily to allow the mass spec to be ready for the next acquisition. On the screen on your right, you will see the blue color, which indicates a sample has been analyzed or has just finished running. The orange, yellow ones are the ones that are waiting for analysis. And then we are moving from sample to sample down the list here. We'll give it a couple of minutes to so the plate just moved again. And again, this is how we proceed from sample to sample. The interesting thing here is that this is all automated, of course, just like you would have for an LC-MS type run. And at this point, the system will only take one plate at a time, but obviously, the next step for us is going to have multiple plates, just like you would have another sampler on an LC-MS environment. As an aside, we're also looking at another option to help us screen. These are screens. Just remember, we're working with toxicology screens here. We're looking at being able to run the same well multiple times. The reason behind that is that if you do a tox screen, you will likely be running different types of assays, illicits, which have a low boiling point, opiates, which have a higher boiling point, benzodiazepine, which have a much higher boiling point, and some illegals like THC that are going to be running even higher in terms of temperature. Why is that important? Well, because in the DART environment, you have to desorb the analytes of interest from the screen into the mass spec. That desorption temperature is specific for different classes. Benzodiazepines are going to be around 400, opiates are going to be around 350, and stimulants, amphetamines, are going to be around 200. So by adding an entire sample on a DART screen, we have been looking at the ability to desorb first the low boiling point. So the amphetamines would come up first at 200. So we'd run the whole plate at around 200 centigrade, followed by rerunning the same plate through the software at 300, 350 to desorb the opiates and opioids, and then moving on to the benzodiazepines at about 400. So the same plate could be actually run 3 times to yield the 3 different classes of analytes. So that is something we're working on right now. It looks promising. We have not done definitive studies. That's coming up next. And sometime between now and the end of the year, we hope to be able to publish some of this work to show that this is a very novel way of doing screens because of this capability of running the same set of sample multiple times. In a way, some similarities with immunoassay. We run the same sample multiple times to look for different classes of compounds, but because this is mass spec data, of course, the quality will be much higher. We'll have a few non-false positives and false negatives, at least, very, very different from what an immunoassay environment would look like today. So now we're going to take you back. We're going to go back for a second, and while we reset the system, and the idea is going to be to show you a bit what the data analysis looks like. I'm hoping we can see it as well. I'm a little fuzzy here on the screen, but we'll give it a try. So let me go back to the slides for a second, and while Terry sets up the system. And so data review. So data review is very important because this is really the only reason we're doing this. We're doing this to generate some data that we can then utilize. Data review here is very, very similar, if not identical, to LC-MS data review. The goal when we first started this project was to fully integrate a DART environment, which again, remember, does not generate a peak, but generates a signal. That signal can have different forms, maybe jagged, and so forth. So we do a little smoothing on it, and we then process it through an LC-MS software, which is a typical software, has not been modified for this application. So we just want to utilize whatever's available, and also we try not to complicate the user's life because learning multiple software is challenging. So ideally, we're going to use whatever's available, and in many cases, whatever people already know. And just to give you a quick idea what that looks like, our data, we end up generating something like that. As you can tell, this has been smooth. The smoothing is not really critical anymore. We've looked at smoothing versus not smoothing, and there may be some benefits from not smoothing. So instead of having the peak that has been manipulated, we just do an integration under the curve or under the area under the curve. And the reason why this may be beneficial is that DART, again, as I mentioned earlier, is based on the elution temperature of different compounds. And even in the same class, you could see, for example, that amphetamine and PCP will have different elution temperature. PCP will be higher, amphetamine will probably be lower. So we may get multiple peaks. We may get more jagged peaks. And we need to get away from this idea of a Gaussian peak because there is no peak here. This is just strictly a signal. So smoothing versus non-smoothing is something that's being discussed right now. And I think going further down the road, not smoothing and just doing the area will be more quantitative than smoothing, which is actual manipulation of data. So without further ado, I'll go back to Terry, and he's going to show us a little bit live what he's been working on. And bear with me because we have to do a couple switches here. All right, I think we're good. And I'll give you the microphone. Yep.
Hi, I'm Terry, and I've been demoing thus far, but I want to show you kind of the data that we get and the similarities and differences from what you might see in a chromatography-based method. So we'll just zoom in a little bit on the screen so that you can see what I'm seeing a little bit better. And I'm starting here with just some raw data. So this is an extracted ion chronogram. Remember, we don't have chromatography here, so it's a chronogram. And this is not a peak. This is just a signal from the detector response. So unlike an LC peak, we're not getting things coming off at a different time, so we're seeing kind of a Gaussian peak. This is just a response for what's hitting the detector and passing through the quads. So just to give you an idea, this is amphetamines. This is following the transition that we've identified as unique for amphetamine. And this is what the raw signal looks like. Now, if we move over to the quantitative data, this is the exact same software we use for LC processing. So that signal that we saw in the previous window is now a smooth peak. So the software uses an algorithm to smooth the peak just like it would smooth an LC peak. So you get this kind of smooth and regular looking piece of data, but just wanted to tell you that it's not a peak. More importantly here is the quantitative data that we're generating. So you can see this calibration was run in duplicate with one QC, and we're looking at amphetamine right now. So you can see that the curve is linear. What you probably can't see on your screen is that the R-squared value here is 0.996, which is as good as you could expect with a chromatography-based method. And it's obviously much, much faster. So this is over a linear range of 125 to 25,000 nanograms per mil for amphetamine, and it's fitted to a linear regression. We have accuracy between 85 and 115 for most of these samples, and our QCs are also between 85 and 115. We can go to another. We can go to another compound. So we're looking now at stimulants, and we can go to another compound that's of great interest right now, which is xylazine. And so I will change this data and look for xylazine really quickly, and we'll present that to you. So the stimulants are good fits for DART because they have high proton affinity, and they fit really well into the DART liquid-liquid extraction workflow. But we also have some compounds that don't have as high a proton affinity that we wanted to show you that can also be analyzed via DART. So we have xylazine here, and this is a good time to talk about the need for an internal standard with DART. So we have xylazine fitted to a quadratic regression model, which is common for these screens. But you can see that some of these data points are a bit off of the curve. We still have an R-squared value of 0.94. When we have an internal standard that's matched to xylazine, we get an R-squared value of 0.99 when it's fitted to a linear regression. So we also see fentanyl here, and with fentanyl, we do have an internal standard that's isotopically matched to fentanyl. So this R-squared value is 0.992. So again, good for LC methods, but also for a rapid screening method with no false positives using mass spectrometry as compared to the common immuno-based assay results. And again, just one more time, this is a chronogram, and we've got our signal, our DART signal, that is smoothed into what looks like an LC peak. And this is just the way that the data is processed. And again, accuracies are falling between 85 and 115. So very similar quantitative parameters as what we see with an LC method, only just much, much faster here. And I'll pass this back over to Francois so he can talk a bit more about the data.
All right, thank you, Terry. That was great. So, limited amount of data here. But it was, like I said, we're working through a lot of these things, but I figured there are some people that would be interested in taking a look at this. We will have some Q&As in a minute. I just want to give you a quick wrap up, and so we have a little bit of time to just talk a little bit more afterwards. DART has been integrated into the Bruker family of mass spectrometers. We've been putting it pretty much on anything and trying to figure out where we can take this next. We've done accurate mass, we've done TOF, QTOF, and timsTOF. So besides the triple quadruple options, of course, we can do a lot of different things. And I just want to walk you through a couple of differences of why these different applications, where they're reaching out, basically. So for the triple quad is really at this point to do semi-quant and quantitative work, which is very novel, and this is why we're taking it slowly, making sure that this works as expected. We get results that are in line with everything else in the quantitation world. But for TOF, QTOF, we have been able to do a lot of the work that had been done in the past, identification of specific compounds and speciation of woods, for example, looking at origin of products, meat, coffees, things like that. Looking for explosives, looking for in forensics world. So there are really tons of application in the exact mass world. And for us, because we have a device that is unique out there called the timsTOF, we've been able to do some really interesting work looking at compounds that are normally would separate or not separate very well necessarily in chromatographic world, looking at the timsTOF to separate them in time or in a trap time environment in the mass spec itself. So that is really for us where we're pushing the limit in the exact mass world, is looking at DART in this TIMS environment, which you'll be seeing a lot of that going over the years. The center in Bremen, Germany is taking the lead on that approach and trying to figure out where we can take this technology next. So this is really, in a nutshell, where we are with DART. We have a lot of applications coming up. We'll be at SOFT next weekend, this coming weekend, actually. So things are moving really fast. And we'll be talking about toxicology approach, toxicology screening, multiple classes of analytes, and where this is going to take us. Forensic toxicology is one big area for us. And of course, the same thing in the clinical tox research environment. And again, we're talking about research here. It's just very specific. I want to be very clear about that at this point in time. There will be publications by some of our collaborators also coming up in the tox world that you will find over the next few months. But this is really exciting time for us. And after SOFT, we have a bit of a lull in a lot of our travels and conferences, which will allow us to stay in the lab and really focus on this project. And hopefully by the end of the year, early next year, we'll have some really interesting development to share with everybody. The next big stop for us after SOFT will be MSACL, where we're hoping to be able to show some much more information as to what we've been doing and the areas in which we've been able to take this technology. So without further ado, we can move to the question and answers.
Great. Thank you so much for the presentation and also for the demonstrations. That was interesting, and it does look like we already have some great audience questions coming in. So before we get started on that question and answer session, I would like to quickly remind our audience how to submit questions. You can submit your questions by typing them in the Q&A box, which can be found directly below the video player. So our first question today, and I am going to apologize for my pronunciation. Can DART-MSMS quantitate NH3, urea, trimethylamine, 2-dimethylaminoethanol, hydroxylamine directly over urine, or is any sample prep needed, like adding base or salting out? And then additionally, do urine levels correlate in any simple manner with blood levels? And what are the best VOC diagnostics for RNS and ROS?
All right. Well, this may take the rest of the time to answer, but so quantitation of yes, I think some work has been done on urea and trimethylamine. I don't know the extent of that work. We can look it up and try to get back to you if you can send us a link so that we can contact you back. I'm sure that's possible. Again, I need more specifics on what's been done in the past. So the question there is quantitate, right? So DART for a long time has been used for pretty much a qualitative type of work. For qualitative work, minimal amount of sample prep is fine. For quantitative work, not so much. So we do know that once we move from qualitative to quantitative, we do need to put some kind of sample preparation. For example, in urine, we have problem with the urea dimers that have a tendency to affect quantitation. So you want to measure urea, so that's probably possible. But the other compounds, because of the urea dimer interferences during the acquisition process, would probably require some kind of sample prep, I would think. Adding a base, salting out is probably not ideal, because if there's any salt remaining in the sample, that's not going to help us. It's probably going to hurt us. So I would say salting out is probably not an option. But pH modifications may be more appropriate here. But basically, I think the best would be some kind of sample prep, at least to remove, a good majority of the urine matrix in there. So as far as correlation with blood levels, I have absolutely no idea. Depends on the compounds. I mean, your urine is an excretion product where blood is not. So what you would have in the blood may or may not correlate with urine. I mean, we know blood and oral fluid correlate because there are related fluids, or so that yes, with oral fluids, yes, and blood, yes, but with urine, I really don't know. I cannot answer that question. So, but like I said, if this is a much longer discussion than we have time for, but if you're interested, we're more than happy to continue discussion over email so far. So the last part here, VOC, RNS. So yeah, that's probably possible. We probably have we done a lot of work on volatiles. Actually, Terry that just spoke to us and showed us did all the prep in the lab. Did a lot of work on volatiles. He did his PhD at Cornell on volatiles. So there may be some relation between these different compounds. Alkanes, alkyde, and alcohol. So that's probably a possibility there. Again, this is a 20,000-foot answer, so hard to give you more details without digging a little bit more into the topics.
Perfect. Thank you so much. And on to our next question. What is the approximate cost of DART-MS system?
Cost of the system. Hang on a second. I don't do marketing too much. I'm more, or sales. I'm more in the lab. So let me check. Yeah. Yeah. So again, this is something we probably want to take offline because it depends on what kind of system, on what platform you're looking at putting it on, and there are a lot of variables. And as you saw, we demoed a system that's called an HTS. It's a high throughput system, which can do 48, 96 wells. There are other systems that do single sample for a specific analysis that do 12 samples at a pop. So again, there are a few too many variables here for me to answer that online.
Thank you. And with this type of screening, how quickly could you theoretically run a 96 plate?
So what we just demoed right now, we ran about, this plates in toxicology runs about an hour per plate, so an hour for 96 samples. That is a very conservative number. We are developing assays right now. We're not optimizing them for high throughput. I would think we can probably drop that to about half an hour per plate, in a reasonable fashion.
Wonderful, thank you. And does this type of screening work with all toxicological drug classes?
Good question. That's what we're working on right now. So we started with amphetamines. We've done some work with opiates and benzodiazepines. So amphetamines and benzodiazepines work quite well. Opiates work well too, but they can be optimized further. We need to get a little bit better results out of our QCs and things like that. I mean, it's not bad. It's just we can do better, I think. Again, remember that this is an environment that requires some sample preparation. So we're working on optimizing sample prep to get better signal, and especially to go down lower in concentration. These are screens, so the levels are reasonably high, but we want to go as low as we can so we can do forensic screen, which are typically much lower.
Great, thank you. And do we see a dose-dependent response with DART-MS signal?
Not necessarily. So that's something that is a little different than LC. In LC, you see that problem too with matrix. So the more matrix there is, or matrix interference there is, the more likely you will not see a dose-specific response because there will be interference. So this is more pronounced with DART than it is with an LC environment. Hence the reason for trying to optimize sample preparation. And again, this is for quantitative work. For qualitative, it's a whole different story. But for qualitative work, we do need to work down that road of sample preparation.
And is DART-MS a quantitative assay?
Well, yes. I mean, that's the premises on which we're working right now. We're tackling semi-quant. We've done some work that shows it is quantitative. Again, Terry's PhD dissertation showed that. So we know that we can do it, and we're working very hard right now to get to that point. So the current work is focused on semi-quantitative as a first step. So once we understand everything that we need to, then we'll take it to fully quantitative.
Thank you. And what are the benefits or challenges of removing chromatography?
So chromatography has been the sort of workhorse for this kind of work for many, 20, 30 years now. The big difference is that in chromatography, we've been focusing more and more on letting the column do the separation and doing less and less sample preparation. For example, in the tox world, I'm doing a lot of dilute and shoot. We just take the urine, dilute it 10 to 20 fold, and do the analysis. And it works fairly well. Why? Because the column does all the separation needs to be done in order to get a quantitative assay. With DART, we've removed separation in between the injection and the mass spec. So we need to do some kind of separation, some kind of matrix removal in order to make this work. And that is basically the sample prep. So the challenges for DART is to go back to sample prep the way we used to do it 20 some years ago. But luckily for us, we have much better technology right now for sample preparation. We can work with SLE, we can work with SBE, we can work with liquid, and we can try to figure out which of these technologies work best for what we're trying to do. And that is the challenge right now, is to go back to what we had years ago and make it work much better, much faster, much cheaper for today's world and today's analysis. And that's what, that's part of what we're focused on right now.
Wonderful, thank you. So on to the next question. Is the desorption temperature constant for each sample well, or does it span a range?
That's a good question. Right now, it is constant. We do not have the ability to do a ramp during the run. That has been discussed. The problem with that is that you need a fast response from the DART in order to bring the temperature up. There are questions of stability and things like that. So for what we talked about today, we do, and that's what I mentioned earlier, we're looking at doing a low pass at 200 degrees C, for example, to desorb certain compounds, amphetamines, for example. Maybe go higher at 300 to do opiates, and go higher at 400 to do benzodiazepines and so forth. So that's a traditional, non-traditional approach to this, where we're doing multiple passes over the same well and getting results that work. There is an option in DART world. This is for single sample only. It's a somewhat, you can think of it as a thermal desorber. You put your sample in this little copper crucible, and that gets heated to about 600 degrees. So you have a ramp from ambient to 600. While this is happening, you can monitor the headspace above the crucible, and thus, for example, look at polymers. Look at polymer analysis. As the polymer breaks down, you can look at you can monitor the breakdown products above the crucible, and thus get a ramp. But this is a very specific one-by-one sample. You cannot do this right now with 96 samples at a pop.
Perfect, thank you. And can you comment on the selection of non-isotope labeled internal reference standard?
Non-isotope labeled. So I come primarily from the toxicology world, where we pretty much have to use labeled ISs. So we do, and that is, it's more expensive, but it's obviously better in terms of matching the drug you're working with, the compound you're working with its internal standard. It's kind of the easy route, but the expensive route. As far as using other ISs, not labeled ISs, really you have to do this experimentally. We've done that a little bit with labeled ISs because it's cheaper to put 1 than 5, obviously. But the idea is to look for compounds that are similar, not necessarily naturally occurring, but similar enough to the compound you're doing, analyzing. Right now, we've been doing this by experimental approach. Really, we don't have a really good handle on how to do this. Just looking at structures, at type of molecule and so forth. So it hasn't always been obvious to me why one compound works better than another at this point. But with time, we'll probably gain a lot of insight into this. We're just starting to look at that right now. The use of ISs is fairly common in the U.S., less so in Europe, and for some, especially for food and environmental. And this is something that we're starting to discuss quite seriously, because there are fields where using label AS is just not common, and there's a cost issue. So this is something that we'll have more details on in probably sometime next year.
Great, thank you. And is there a way to account for isobaric compounds, so like morphine or hydromorphone, for example?
That's a good one. Yes. So remember when I talked about timsTOF? That's it. So timsTOF has the ability to separate isobaric compounds. So as you know, in LC-MS world, we have to separate them. Actually, the law right now for running toxicology, clinical tox samples requires that the confirmation be done via chromatography, because if you don't separate those compounds in time, you cannot separate them in mass because they're the same parent mass and the same fragments. The ratio between fragments may vary, but the second you have a blend of morphine, hydromorphone, or hydrocodone, you cannot tell what percent of which is which. So that cannot be done with DART right now as it currently stands. There is some publication coming up from Yale University. Keep your eyes on that. Should be coming up sometime this fall, is my understanding, where they actually looked at that. They looked at doing this kind of work, and they did discuss that. So I won't steal their thunder. Just keep an eye out for Yale University. Joe El-Khoury has something to say about that coming up. What I can tell you down the road is trying to utilize the TIMS cell, which allows the separation of compounds by a cross-section. So this is an electronic separation in the mass spec, and we've been talking about that, looking into it. Right now, it's still theoretical. Should work, but we are yet to try it in a toxicology environment specifically.
Thank you. Moving on to our next question, beyond the elution temperature, what steps are taken to confirm what signals correlate to what drug type?
I'm sorry, can you repeat that?
Yeah, absolutely. Beyond the elution temperature, what steps are taken to confirm what signal correlates to what drug type?
Okay, so basically, just how to optimize the temperature at which you will run a specific compound, experimental at this point. I mean, you can guess by drug type, drug class, but again, within the same class, for example, if you assume that amphetamine, methamphetamine, MDMA, and PCP are related compounds, you'll see a gradation in temperature as you go up the molecular weight scale. So that's one way to look at it. But honestly, the easiest way to do that is experimentally.
Perfect, thank you. And is the software integrated to control the DART and the MS?
So the version that we demoed today, no. The next version that we're releasing a new platform at Soft, and that one is fully integrated. That one will be a complete integration of DART. So think of it as DART as another source. Instead of having a HESI or an APCI, you can have DART. And those source parameters in that new software are fully integrated.
Perfect, thank you. And what is the equipment you used for the liquid-liquid extraction?
Well, the equipment we use is very simple. I mean, by equipment, so we use this ToxBox from PinPoint. PinPoint labs out in Arkansas. So we've been working with them quite a bit to try to help simplify the whole workflow. As far as equipment to do this exact process, you're looking at pipetter, multi-channel pipetter. You're looking at a blow dry system of some sort. You're looking at a heater shaker. What else? Am I missing something? And I think that's it. It's very basic. I mean, most labs, that will start in toxicology would need that no matter what. So we're not adding anything new to the equation. There's no centrifuge, which is a huge cost factor here. The liquid makes that unnecessary. So that's about it.
Great, thank you. And can this source be hyphenated with MSMS from other manufacturers?
Yes. So IonSense was an independent company for about 15 plus years, and IonSense was acquired by Bruker in the spring, and decision was made to continue to sell that source to other vendors. So obviously, the improvements such as the integration of the software will happen primarily on the Bruker system, which it did, whereas with other systems, it's less likely to happen. But it will. We have a fairly large customer base with pretty much any other mass spec out there, and that will continue for the time being.
Thank you. And is there any concern of thermal degradation of the analyte in the source?
So by the source, you mean the DART itself? That, of course, that's an issue that to be considered. The source behind DART, in other words, what used to be the source and doesn't really have any heater in it, but on the DART screen, if you analyze thermal labile, then that's something that needs to be considered and evaluated prior to doing analysis. But that would be part of your method development, as every new drug compound will have to be developed to some extent. I mean, it's fairly small development work, but the DART part needs to be evaluated because some compounds, of course, may not survive that.
Great, thank you. And what are the benefits of using DART over other systems that may provide both separation and library identification without any sample prep?
Right. So, well, the reason DART is moving on to the so we're part of the applied markets at Bruker. The only reason DART is moving into the applied markets at Bruker is because there is a demand for simpler, faster, cheaper system. Simpler. Well, an LC-MS is a much more complex platform. I spent a fair amount of time in my life consulting, and most of my problem came from the LC. The LC is a complex machine. It breaks down, it clogs, you have to replace things. DART is a very simple machine. There's not a lot that can break down in DART. Either it works or it doesn't. There's not much in the middle. So it's much easier to operate. You don't need advanced degrees. DART is very straightforward to operate. It's also much cheaper. We're seeing big demand in some part of the world because people don't want to be buying solvents, which are pricey, and then disposing of solvent, which is also pricey. So there's a speed, there's an economics issue there, and it's also a green solution. Today's world, we're trying to figure out how to limit the problems that we're inflicting on the world, and that's one way to do it. Less solvents, less disposal, less components, less consumables. So those are the three really big push forward. And here, at Bruker, we're actually spending a lot of time and effort right now looking at these chromatography-free workflow, which means LC-free workflows.
Excellent points. Thank you. And what is the maximum number of transitions for one sample according to a MSMS detector?
As with DART, because everything is being analyzed or being introduced at the source at once. Right now, with the machine you saw, the mass spec you saw, which is our entry level, the elite, you're probably looking at 6 to 12 compounds per panel in a sustainable, reasonable fashion right now. The next machine up will probably double or triple that, I would think. So it's really a question of how much power, resolution power your mass spec has. The more resolution power, the more you can add into your sample. Whether you want the 4-cylinder, the V6, or the V8, that's really where it's at right now. The more power you have, the more transition you'll be able to look at simultaneously.
Great, thank you. And it looks like we have time for one more question. So to wrap up, would you recommend to use a DART source instead of an LDTD source?
LDTD source, yes, sure. That's a good question. We have not done a lot of head-on comparison, and my experience with LDTD is somewhat limited. I mean, I've come across it over the years. I can't really answer that too much right now. I would think DART may have some, it's easier to use, I would think. The LDTD is things a bit more complicated. But again, that's something I don't have a lot of experience with. I would have to do some head-to-head comparison. So I don't know that I can really answer the question at this point.
Perfect. Thank you. Thank you for the presentation and also for taking the time to answer all of those great audience questions. With that, it does look like it's already time to wrap up. I'd like to thank the audience for attending and participating in today's event. And I would also like to thank our sponsor, Bruker, for making today's educational webcast possible. We would like to ask everyone in the audience to participate in a brief survey that will appear on your screen after today's presentation has ended. You will also receive an email alerting you when this webcast will be available for replay, and we invite you to forward that announcement to your colleagues who may have missed today's live event. We hope to see you all next time. Thank you and take care.